Hello. Today we're going to be covering wave-particle duality. Firstly, we're going to talk about some of the properties associated with particles and waves. Secondly, we'll be describing the electron diffraction experiment and explain what is suggested about the nature of electrons. And finally, we'll perform some calculations with de Broglie's equation, including momentum calculations. To start with, there are several phenomena we should be familiar with in order to fully understand today's lesson. For example, we have reflection, refraction, interference, diffraction, polarization, and the photoelectric effect. Some of these phenomena can be explained in terms of waves and some in terms of particles. For example, reflection and refraction can be explained in terms of waves. However, there are some explanations in terms of particles as well. On the other hand, we have interference and diffraction. These can only be explained in terms of waves. Let's familiarize ourselves with interference and diffraction before we get started. Diffraction is where a wave is passed through a narrow slit. As it's passed through this narrow slit, it will spread out and form what's known as a diffraction pattern. In order to observe diffraction, the wavelength of the wave should be roughly equivalent to the size of the slit it's being passed through. The other phenomena to understand is interference. Interference occurs when two waves overlap each other. When these waves overlap, they can either interfere constructively, in which case we get an increase in the intensity, or they can interfere destructively, in which case we get a decrease in the intensity. Interference and diffraction can only be explained in terms of waves. Because of this, if we observe something undergoing interference or diffraction, we can assume it's behaving like a wave. And this was exactly what was observed in the electron diffraction experiment. In this experiment, electrons are accelerated by a device known as an electron gun to very high velocities. They are then passed through a thin graphite target where they were observed to spread out or diffract. Finally, the electrons reach a screen where they were observed. At this screen, we see an interference pattern of maxima and minima consistent with constructive and destructive interference. In this experiment, the electrons were seen to both diffract and interfere. The conclusion was then that the electrons could exhibit wave-like properties as well as their known particle-like properties. This was the idea behind wave-particle duality, that certain objects like electrons could behave as both particles and waves. Here's another question for you to have a go at. Pause the video and jot down some answers to these questions. My answers will shortly follow. And here are those answers. The first answer is that electrons can exhibit both wave-like and particle-like properties. And the second answer is that this is demonstrated because electrons diffract and interfere. What's interesting is that wave-particle duality was hypothesized before it was confirmed by electron diffraction experiments. In 1924, Louis de Broglie suggested that all particles could behave as waves. He also deduced that the wavelength of a particle was inversely proportional to its momentum. It's important to remind ourselves as well that momentum of the particle p is equal to the mass multiplied by the velocity. Subbing this into the first equation, we get that the wavelength is inversely proportional to m and to v. In this equation, h is again equal to Planck's constant. Here's another question for you to try. I'll leave the equations that you need on the screen and ask you to pause the video and write down the answers. My answers will follow shortly. And finally, here are the answers.